Hello, everyone. Welcome to our CS225 final project presentation. Next slide, please. My name's Sahan Kumarasinghe.
I am Prakarsh Gupta.
My name is Rishi Choudhary.
My name is Sreekar Bathula.
Starting off with the goals of the project, we essentially divided our goals into three main parts. First one was the Wikipedia game. So essentially, the Wikipedia game is a game where the players try to get from one specific page to the other in the lowest amount of time possible, and we plan to create it using a C++ program. And we also implemented graph algorithms to better understand the Wikipedia data set and find the shortest paths between the nodes, and benchmarking so that we could test out algorithms and perform as if they're expected or not. Next slide, please.
Coming to how we got the data, we downloaded the data set from Stanford Snap, which you can find on the CS225 website as well. And we had two different types of files for the vertices and the edges. The vertices was a CSV file and the edge was a TXT file. And the vertex, each Wikipedia page had a unique node ID and a page name. While coming to the edges, each edge was represented as two node IDs separated by a space, where the first ID was a source and the second ID was a destination. Next slide, please. Coming to the overview of the algorithms we used, the traversal we used was a BFS, a breadth first search. And we implemented the BFS over disconnected components as well as the complete graph ADT. And we also, coming to Tarjan's algorithm, we for strongly connected components, we used Tarjan's algorithm instead of Kosar's algorithm, and employed the algorithm to find the SCC in the graph. And coming to the landmark path, we used our shortest path algorithm in our BFS traversal to solve the landmark path problem. Next slide, please.
So a brief overview on testing. We use Catch2 for most of our testing. We tested against hard-coded structures in the actual tests, like cycles, trees, and combinations of them. We tested against known data generated from our Python script, which was especially useful for verifying SCC generation for large graphs. We also generated a binary so that we can easily time our algorithms so that we can make sure that the runtime we expect is the actual runtime. And we developed a Python script, make-mock.py, which uses the NetworkX module to automatically create fake graphs whose properties we know, especially the number of strongly connected components and membership of it. Next slide.
So coding graph ADT, we coded the graph ADT as an adjacency list. The adjacency list was basically created as a hash map containing other hash maps. So a vertex would point to another hash map whose key would be vertex and would have a value of an edge. It was based off of LabML with certain modifications. We did that because it provided us suitable runtimes for our most important four functions: incident vertices, adjacent vertices, insert vertex, and insert edge. It also allowed for an easy API to create other important functions such as get BFS, get shortest path, get landmark path. Um, Moving on. So we tested graph ADT using two important functions, display graph and save PNG. So display graph essentially displayed the graph as an adjacency list, while save PNG displayed the graph as how the graph would actually be drawn by hand. Um, we also tested using catch2 against expected responses. For example, insert vertex would give insert vertex on four vertices should have created four entries in a hash map. We tested similarly for insert edge and remove vertex as well.
So for coding the BFS traversal and the full BFS, we implemented a class BFS traversal as a wrapper so that it's reusable and it's better for memory than a full vector. And we have a nested iterator class, which is the actual iterator that does the traversing. And we have a full BFS, which inherits from BFS traversal, which only does the connected one. And we have a nested iterator for full BFS as well, since the only difference was the operator plus plus method. Next slide. And for testing full BFS, in the beginning, we looked at quadratic time, but this was because of how we were inserting new disconnected vertices to the traversal. Once we remedied this by maintaining an external set, we started seeing linear time once again. Next slide.
So coding and testing strongly connected components. We detected strongly connected components using Tarjan's algorithm. We chose Tarjan's algorithm because it was the superior algorithm for us compared to Kosaraj's algorithm, because Kosaraj's algorithm required a reversal of all edges, and also Tarjan's algorithm worked better for us in a real life scenario. Um, One notable thing over here is that the strongly connected component graph inherits from our original graph class. So so it provided us a way to use all the inherited functions such as get shortest path, get landmark path, etc. Um, One important thing over here was that using SCC graph, we were able to obtain a directed and an acyclic graph containing only the strongly connected components, which is depicted on the right hand side of the slide.
As evidence from our data, our SCC graph data structure saw linear time in construction. Next slide.
Coming to coding and testing the landmark path, which is our third algorithm, we implemented it as returning a vector of vertices to visit, which was the most straightforward way of displaying the results. We also used unordered maps to keep track of the previous vertex. And since it was heavily dependent on BFS, we had to add another method called arrival edge to determine the vertex persistor. And we also heavily refined the get shortest path method and the BFS iterator in order to code a landmark path. Next slide, please.
So through all this coding and testing, we were able to execute all three of our algorithms successfully, and also input validation by also pass it all test cases, and we were able to correctly read handcrafted data and the mock data. Next slide, please.
So some interesting results and unexpected outcomes from our project were that we found out the largest connected component, which is 45,486. This is the largest strongly connected component that we could detect on our computers as well as EWS computers. Uh, so we couldn't load all the edges, but this was the largest strongly connected component that we found. Another general pattern that we found was that strong connectivity between nodes suggested context similarity. So in the following tables on the left hand side, you can see that it's a strongly connected component, and it they all share a common context of figure skating.
So, it, talking about some challenges here. So we switched from A star to die star at the first start of the semester, start of the project, sorry, and then switched from die star to detecting SCCs. And then we also had some problems with booleans to mark an empty edge because they were using so much data. And for the last one, for failed SCC optimization, as you can see the figure on the right, if you need to go from the green node to red node, the shortest path yielded by the SCC graph is not the actual shortest path. Instead, it's the shortest path between the two SCCs.
All right, so this is the demo of our final project. And as you can see over here, we can run our final executable file, WikiQueria, over two arguments, a vertex file and an edge file. We can also specify the number of edges we want to load, but in this case, in our case, we're just going to run it over the complete files. I've previously prepared some files to run the data, run the program over, and let's go ahead and see what we actually get from that. So here is an interactive tool with a couple of options we can explore. But for brevity's sake, we're only going to go over the most important ones, which are print full BFS and find shortest path. So let's go ahead and actually print the full BFS and see what it looks like. So as you can see over here, we have a list of 60 vertices in the order of the BFS traversal. Now let's go ahead and use this list and find the shortest path between two random nodes. So let's say we pick any two random nodes, for example, this one and any random one, let's say this one. So you can observe over here that the number of edges in our shortest path is 5, and it also gives us like the number of links we need to click on to actually get to this final page.
And talk about some of the reflections of the project. There are four quotes here, but I would like to highlight the one that implementing the Wikipedia data into this project was a super cool experience. And I speak for the team itself that we had a really great experience where we would learn a lot and execute a lot.